Hello everyone, I'm Tamás Lovas from BME and this is the Capturing Reality module. At this time, we'll talk about the use cases of terrestrial laser scanning. So there are different application fields we can use terrestrial laser scanning. I think this is the best way to understand what is the potential of this technology, what are the advantages of the technology if you are glancing through the main application fields, which is capturing the geometry of cities, buildings, both indoor and outdoor, bridges, pavements using in engineering geology and capturing the geometry of complex facilities. I will show you some examples of each. So for the cities, we are capturing the geometry of the building facades, of the roads, of the road furniture, for example, for autonomous driver simulations. So that's a very important and hot topic today. In case of building survey, we can capture the facade from outside of the building. You can see what kind of resolution, how good resolution we can get even from a mid-resolution laser scanning survey. And this is the facade of the main building of BME. You can see the white areas there that are the occluded areas. So obviously, if you want to capture the full area of the facade, you need to apply multiple terrestrial laser scanning points or combine the laser scanning with drone photogrammetry. If you are doing indoor survey, you can use the Google API to create a Street View-like data set, and you can walk around in the data set and check the building inside. That's an interesting project because this is a railway station building in a small town, and it was covered in a very expensive tiles, and they were curious about the geometry of the facade because a very expensive glue is to be used to attach these tiles to the facade, and we captured the geometry of the facade, projected a plane, and derived the deviation map with an open source software between the ideal plane and the laser scanned real facade. This is an example of capturing a building from outside and from inside. And as you see the geometry, there are steep slopes and very tricky distances to capture the outside geometry from terrestrial laser scanning. So therefore, we used photogrammetry. As you see the positions of the UAV images from above, from the air, and we captured the geometry of the building with terrestrial laser scanning and derived 2D products for architectural survey. We also derived orthophotos from inside. For architectural historical documentation, they need to map all the walls and using legends and draw all the stones, contours, and legend them whether they have a carving or cracks on them. And we provided the geometrical data and the orthophotos to this kind of architectural documentation. In this case, we captured the geometry of a bridge, and the main point was to measure the displacements of the wall at the head of the bridge, and for that we created the BIM model of the bridge from the design plans, captured the current geometry by laser scanning, and combined them in Cloud Compare in an open source environment, and derived the deviation map. And at the end it turned out that there can be even 20 centimeters movements or displacements observed. In case of bridge survey, we use laser scanning for bridge load tests. So after the bridge is built, is created, it goes under a load test. So they put loads with several trucks on it, and we measure the displacement of the pavement and the movement of the pylons. And since we are using a surface like technology like laser scanning, and we capture the entire surface of the bridge, combine the pylons, the cables, the pavement, the girder, all the structural elements, we could analyze not only the movement of the pylons, but the deformation of the pylons, the movement and displacement of the cables. So we provided a much more sophisticated and detailed analysis compared to the traditional surveying methods when we're measuring displacement in discrete points. That was a project capturing the ship hull of a barge, because they redesigned the front and the back part of the barge. And the tricky part was that this barge was black, so it's not a reflective surface. So we need to use upscale laser scanners to capture the geometry. But at the end, we provided the geometrical data for the hydrodynamic simulations. In case of these measurements at a castle, we captured the geometry of the rock walls of the castle, because rocks were falling down. It was dangerous. So we captured it from the ground with terrestrial laser scanning, and combined the laser scan data with UAV photogrammetry with imagery, so not drone laser scanning. And therefore we captured this geometry in February, when there is a leafless condition of the vegetation. But at the end, we needed to derive the geometry, the 2D sections of the rockfall facade, and then it was used for engineering geological applications. The same in case of open pit, when we derived the fault planes of the pit, and it was used for analyzing what kind of materials, rocks are there underground if they want to extend the open pit. Okay, this is a project capturing the cable car of Budapest, the walls of the cable cars. The first data what was available is that there are certain cracks on these walls. So they tried to get geotechnical survey of them. They needed the geometry, but since they didn't know the exact location of the cracks, they just see some cracks here and there. They wanted to capture entire geometry. So that was that's why the final solution was laser scanning. So we laser scanned the entire wall sections and projected ideal planes and created the deviation maps compared to the ideal planes, and we derived where are the biggest differences, and then the geotechnical experts could make their surveys. In case of road pavement surveys, there are many kind of malfunctions or errors on the road pavements, like cracks or waves or displacements, and we use laser scanners for that. But at the end, so we captured the entire geometry of the pavement, which is again a tricky task because of the color. It's black, so it's not reflective. And second, we have low incident angles, so we need to use multiple scanning stations to capture the geometry of the entire road surface. But at the end, we needed to derive 2D products for the engineers, or even deviation maps that shows the condition of the road pavement. That's another interesting project in case of a stadium. So we captured the pavement under the running track, which they needed a millimeter accuracy road surface model about that pavement. So we used upscale laser scanners and traditional land surveying methods to provide this kind of surveys. The same similar task, where the same accuracy demands in case of a test track, a road test track in an aquaplaning basin. We created the model of the basin bed of this test track by terrestrial laser scanning, and we derived open CRG models that enabled autonomous driving simulations. In case of water treatment, we are talking about very complex structures with multiple pipes, so it's almost impossible to capture the geometry with traditional land surveying methods. So we use laser scanning, and there are multiple software enabling automatic pipe detections, so fitting cylinders on the point clouds. So then at the end, for example, Edgewise is a perfect tool that to that. So at the end, we have the 3D model of the facilities. So if you want to evaluate the terrestrial laser scanning, the main advantage is it works day and night, and indoor or for example in a tunnel. It's not sensible to shadows and sunshine. The color information can be captured simultaneously. I showed you some example that we are using that. Think about the 3Q-like application. It has a scalable resolution, And again, I repeat myself, we produce a huge amount of data, so we need computing capacity, and occlusion problems can occur during the data capture. That's why we need to apply multiple scan stations. I collected multiple sources, references for this module, so feel free to check them. And thank you for your attention. In the next video, we will talk about mobile mapping. Thank you. Goodbye.